All right, my name's Kyle. This is my Stat 323 Project 2, and I'm doing it on the equal variance assumption. Now, I'm doing all this off the cuff, so bear with me. What I'm using for this is I'm actually using my Project 1 dataset. The goal of Project 1 is basically I threw projectiles at Quentin Tarantino. It was a play on the whole you chuck tomatoes at someone when they're bombing on stage. So what I did is I just picked 5 what I thought were funny objects to go ahead and chuck at his face. I used M&Ms, pretty standard, something everybody has, grape tomatoes, Donald Trump playing cards, just with everybody calling him violent, condoms, and then I also used sausages. Now, thing is with this experiment, if we just take a look at the data, sausages all have very low values, basically next to 0. So there's not going to be a big variance between the data. But when you go ahead and look at condoms and trump cards, and granted I should have seen this coming when I did the experiment, but their values are so much higher, just naturally. I mean, look at the gap, 70 to 51. That's a big gap in the data, okay, especially when you compare it to 0 to 4 is the biggest spread here. So the variance for the sausages is going to be much smaller than the Trump playing cards. Now, the equal variance assumption within the ANOVA, the reason why this is important is because part of the calculations for how the ANOVA is actually run involves pooling the variances together. So when you have big data points like this with a big variance, and you pool it with the variance of the sausages, which is very small, what's going to happen is the gap between the sausages, the M&Ms, and the tomatoes is not really going to show up, right? Because now the pooled variance is going to be much higher than what it should be if you only accounted those 3 variables. And it doesn't make any sense to think that how I throw my trump cards has any effect on how I throw my sausages, my M&Ms, my tomatoes. So what I went ahead and did is I ran 2 different analyses. One, including the trump cards and the condoms, including all the data points. And then the other one, only including in the sausages, the M&Ms, and the tomatoes. Let's take a look. Okay, so let's run through this first jump output. As you can see right here, the gaps between the Trump playing cards and condoms, there's just no overlap. A little bit of overlap here on the bottom of those condom data points with the grapes, the M&Ms, the sausages. But the main thing we want to focus on with this output here is the spread. Look at that. So all these are fairly close to each other, and these very wide apart. And we can see that, look at this, standard error 2.09. That's the pooled standard one, 2.09. But then we look at this, 7.23, 12.17. These big numbers are pulling up the pooled standard deviation. Okay, and when we look at the equal variance assumption, we see that this fails miserably. All the tests across the board. Now, here's some numbers to memorize for you. As you see, all these are significant. This doesn't really matter up top. All these significant ones. This is the difference we're looking at. Sausage M&M, sausage grape tomato, and M&M. 0.986, 0.996, and 0.999. So these are virtually identical. Now, what happens when we go ahead and get rid of the trump cards and we get rid of the condoms? Well, what you're going to see is that the pooled standard deviation is going to go ahead and go down, and that's going to emphasize the gaps between all these 3 remaining variables. Okay, taking a look at this second jump output, first thing I notice is that the variance look more equal right away. Second, now I can start looking and I can see little gaps in between the sausage, the M&M, the sausage, the tomato. Not much, but there might be something here now. Whereas in the last one, it looked impossible. So let's scroll down. Look at this right here. 0.789. This was 2.09, I believe, in the other one. So it's gone down to about 35% of what it used to be. Okay, now check this out. O'Brien, Brown Force, Levine, Bartlett. They all like us. They don't see anything wrong with this assumption. High p-values here. It looks phenomenal. Now, if you had the numbers memorized, they're coming up. There we go. So let's compare and contrast. In the old model, p-value of 0.986. In this model, we got a p-value of 0.384. Okay, still not significant, but that is a very big difference. That had I not made the change, had I not corrected that equal variance assumption, then I would not have even known the difference this large. Yeah, still not significant. Like I said, this is very, very big difference. Here we go. Grape sausage, 0.6061. This was 0.9962. That's almost 1. This is nowhere near 1. Okay? Huge gap. Last one, 0.9235. This one was 0.9999. So in the case of this experiment, I hope it illustrates that when the equal variance assumption is violated, it's going to affect you in two different ways. What it's either going to do is it's going to make small gaps like this. It'll inflate the variance, making small gaps like this virtually undetectable. Or sometimes there will be big gaps and you'll have some low variance variables mixed into there. And that's going to shrink the variance down. So those big gaps look more significant than they are, giving you a false positive. Okay? So, like I said, it doesn't sway these results in this experiment, but you could very easily see how it may have. Hope that helps. Peace and love.